I'm going to do a problem now from chapter 11, which has to do with chi-square testing for the difference between two proportions. And it's from section 1 of chapter 11. This problem is from page 394, and it's problem 5. And this is similar, actually. The data is very similar to a problem that we recently worked. And the problem we just, on one of my other examples, if you look back at that, you can kind of see this problem versus that problem, and it'll make it a little easier to understand. Problem 1029, which was on the previous video example, uses the same data, but now we're in chapter 11, and we're doing 11.5, which again is the same data, except we're going to do it differently, and I'll explain why we're going to do it differently here in a minute. So if you look at the information, it says, an online survey asked 1,000 adults, what do you buy for your mobile device? The results indicated 61% of females, 39% of males answered clothes. The sample sizes were not provided, so let's assume that they are 500 for both males and females. All right, so what we're going to do here is we're going to answer in part A, is there evidence of a significant difference? Notice it says difference. And maybe I'll back up even before I get into this problem just a minute. If you remember the problem, video example problem 1029 that I just did, it had to do with two groups, no means, no standard deviations, so we did a z proportion problem on that data. The reason we did that because it passed the test for normality, which is n times p and n times 1 minus p, or n times pi and 1 minus 1 minus n times pi, n times 1 minus pi. Both of those products have to be at least 5 to use a z proportion test. This test, which is a chi-square test, can be done on a non-normally distributed population. So if our situation says that we do not have a normal distribution, we can't use a z proportion test, and we have to use a chi-square test. So this problem will demonstrate how to use chi-square with that same set of data, and then we'll talk about comparing the results, as it says in part D, the results from this problem with what we had in problem 1029 in the other video example. Okay, so here's our data. This is the information. We have it in what we call a contingency table, which means that we've got cells in the table. We have two options over here. Yes, I buy clothes from my mobile device, or no, I don't. And these are the numbers that they started out with in part A, so that's what we're going to go with. Okay, so here's my step 1, null and alternative. Pi for males is equal to pi for females, and then the alternative is pi for males is not equal to the proportion for females. And again, what we would have here in terms of words would be proportion of males and the proportion of females who buy clothing from their mobile device is the same, and the alternative says the proportion of males and females who buy clothing from their mobile device is not the same. Okay, these are the sample sizes. This is the alpha level that they specified, 0.01, so I have to use that level. Okay, here it is in part A. 0.01 is the level of significance. Okay, part 3, determine the appropriate test. So again, why am I using this test instead of using my z proportion test? Because we're testing for the difference between two proportions, and the information, or the form of the information we have, is in what we call a contingency table, which just means we have rows and columns in this table, and the numbers are placed within that table. The other way we would know to use this approach is if the problem said the data are not normally distributed. Okay? And notice the hypothesis always has to say equal and does not equal for this kind of test. So we're testing for the difference between two proportions, and we have a contingency table. That's why we're using a chi-square test. And If the populations are not normally distributed, that's what we have to use because we can't use Z proportion again. All right, here's our results. And this is our printout from PHStat. It is a chi-square test. You'll notice it says buy clothes from their mobile device, yes or no, and then gender, male and female. So we plug in the numbers that are in the table, just like they were over here. There are the numbers. So we use those same numbers and we put them in over here. And then the computer will provide me the expected frequencies. And it tells me if the proportions are the same, I would expect the number of males and the number of females to be buying clothing from their mobile device to be the same. So that'd be 250 out of 500 and 250 out of 500 for each group. Okay, so that means the proportion of males and females who buy clothing from their mobile device is 50%. Level of significance, 0.01. Problem gave me that. Number of rows and columns, 2 rows this way, 2 columns this way. Remember, a southern mansion has columns and they run up and down. That's how I remember. These are columns, these are rows. So 2 times 2 is going to be 4. And I take rows minus 1 times columns minus 1. So that gives me 1 degree of freedom. And so then I can look down here to get my results. The critical value is 6.635. My calculated chi-square value, which is quite large, is 48.4. And my p-value, you'll notice, is 3.48 e to the minus 12. So what that means is there's 12 decimal places. I moved my decimal point here 12 places to the right, and I put a bunch of zeros in there. So I'm going to reject the null. Now you'll notice for this kind of test also it says expected frequency assumption is met. For a chi-square test, expected frequency values have to be at least 5. And they are all, in this case, 250, so they're a long way away from 5 because we have a large sample size, so we don't have any problem. If we don't meet this expectation, what you would have to do is either combine rows or columns, which I can't do because I only have 2 rows and 2 columns, or I could increase the sample size to get those expected values to be at least 5. The observed values can be anything we want them to be, but the expected values have to be at least 5. So that's what it means when it says expected frequency assumption is met. Okay, so here's the numbers I'm going to work with. Let's go through my 6 steps. That's step, I already had step 1, 2, 3. Here's step 4, determine the critical value. So the critical value comes from my PHStat, 6.635 is my number, and so that goes in step 4. Step 5 is my calculated value for chi-square. This is the formula we're using. The computer has done the calculation for me, so I get 48.4. That is much greater than 6.63, so therefore I'm going to reject the null. Step 6, reject the null. Based on a significance level of 0.01, we have sufficient evidence to conclude that the proportion of males who buy clothing from their mobile device is significantly different than the proportion of females who buy clothing from their mobile device, or at least that's what they said. So the proportions are not the same, therefore I need to change policy. This is still part A, that's step 6. The p-value that corresponds to this, remember, is found on my printout, 3.48 e to the minus 12. So that means I've got a whole bunch of decimals over here, about 11 zeros, decimal, 11 zeros, 348. So it's very close to 0, and therefore, since it's less than 0.01, that's why I'm rejecting the null. I can have nearly 100% confidence that the proportion of males and females who buy or said they buy clothing from their mobile device is different. Okay, so that's part A, and that's part B. What if we change the numbers from what they were before to being the new numbers? 270 and 230 were the numbers that we have. 270 males said that they bought their clothing from the mobile device, and 230 said they did not. They compared to what we had before. Notice we had 195 and 305. So those are different numbers. 270, 230, instead of 195 and 305. How much difference does that make in terms of our answer? All right, so we go through our 6 steps again. Proportion of, that says pi, which is not correct. Proportion of males is equal to the proportion of females, and the alternative is those proportions are not the same. So N1, and for males is 500, and for females is 500. Alpha is 0.01, that's step 2. We're still looking for the difference in 2 proportions, and we have a contingency table, and the population is not normal, so we're going to use chi-squared. Okay, step 4, critical value is the same, but notice calculated value is not the same, and that's because my observed values and my expected values are not the same. So I've got 5.013, which is less than my critical value, and therefore I must fail to reject the null. Okay, so if alpha is 0.01, we do not have enough evidence to conclude there is a difference between the proportions of males and females who said that they buy clothing for their mobile device. Okay, notice the p-value is also different, 0.025161. That value is greater than 0.01, which is why I'm failing to reject the null, and there's not enough evidence to conclude a significant difference in the proportion of males and females who buy their clothing from the mobile device. So, do not reject the null is my conclusion. Now notice, if you look at your p-value, 0.0252, it is between 0.01 and 0.10. That means my answer is sensitive to alpha. So instead of using 0.01, if I change my alpha level to 0.05 or even 0.03, I would be able to reject the null. So I could have 97% confidence, but I could not have 99, which is what I require with an alpha of 0.01. So that's why I'm failing to reject the null. So now what we want to do is we want to compare the results of this problem with problem 1029, parts A, B, and D, which are the previous one that we worked on page 346. So our conclusion is there's no difference in the results. The 2 tests do not reject the null when we use 270 males. The p-values are pretty close to the same. What do I do if they don't come out the same? One of them is assuming a normal distribution, that's the Z proportion test, and the chi-square test is not assuming a normal distribution, or it's giving me my data in terms of contingency table. If the results of the Z proportion and the chi-square test would not be the same, you would believe the results of the Z proportion test if it was normally distributed, which you determine by doing the test for normality, n times pi and n times 1 minus pi. And if it is not normally distributed, I would believe the results of the chi-square test. If they turned out differently, that's how I would decide between them. Now another difference between Z proportion and chi-square is the Z proportion test can be a one-tail test, whereas chi-square can only test for a difference. Are they equal or are they not equal? And of course the way you determine that is the higher the value of chi-square, the more likely it is that I will reject the null. But for the Z proportion test, if it's a 2-tail test, you divide alpha by 2. If it's a 1-tail test, you do not, as you remember. Okay, so in this case, the results turned out the same, but this is the difference in when do I use them and which results do I believe, if they come out differently.